Okay, so I'm going to call up the speakers and representatives of the companies that brought the speakers for our panel, and we'll then convene our Q&A. I think we have two mics roaming around out there. So whoever, we'll start with, the questions, and then one of the ARC folks will be passing out the microphones. So. Okay. So we can go ahead and start with the questions.
Thanks for the good presentations. What I feel a little is, as a contrast, is that Audi, I would say, and is more looking to standard components in that sense. And Albert here is showing us it should not be standard, it should be security from the scratch on. So this is I see that as somewhat as a conflict there. Yeah? For not all PCs will have this security, so you cannot that easily add the functionality like the hardware like you want to have. How do you see that this is merging, I would say?
You want it, Albert? You want to take
Maybe I'll start to try. I think, first of all, the security, I have the mic still hooked up, so. The security is key. We have to make sure that the data points we react on, if we steer the process, are correct and nobody tampered with them. So yes, this is something we need to ensure. The orchestration level I was showing is actually already one level up from where do you get the data points to. And if you now think of how cloud infrastructure works, how Amazon is doing this compute, you have to take this security key exchange, essential key storage, and all of these things you have to keep in mind when you set up this orchestration layer. And in this orchestration layer, you get close to the machine, but not onto the machine itself. The machines itself will probably still have their own control units. And the latest at that point, you need to have keys installed on the machines that identify the machines correctly, that you use for signing, for transmitting data. And there are all kinds of technologies out there, if you just look at it, that you need to build into your system. But I think this doesn't take anything away from, once you get to the upper layers, to the orchestration, you need to have open source systems that help you doing that, but you need to keep the security in mind if you want to start steering your processes.
Dick, I have a comment. Dave Sequino, I'm Albert's strategic security partner. A lot of the technology, the provisioning technology you saw on Albert's slide comes from us. And a couple comments, and I tell a story about the U.S. Navy and many countries' navies. If you look at the world and you look at the globe, most of the globe is covered in water. And there's not enough money in the world to secure the whole ocean. So you really have to decide what your assets are and what your threats are. And you have to partition the world. So in my world, we partition the world in design and development, manufacturing, and service. In Henning's world and in the process control world, you have to look at your assets. And there was a good talk yesterday by Chevron where they looked at the processes that they could secure. Some of the technologies that Albert didn't talk about is our parent company, Greenhill Software, has the only EAL 6+ certified operating system in the world. And think of it as a substrate that can run on standard hardware and create separation. EAL 6+ is an NSA certified specification that talks about a separation kernel, which means it's as good as an air gap. So there are technologies out there, and Henning talked about his virtualization, right? So there are ways to create separation in a way where Henning, he might have critical processes that are safety critical, right, that absolutely need to be secure, but a lot of the data coming off his manufacturing floor doesn't have to be absolutely secure. So if you look at the world like an ocean and you say, you know, there are safety critical applications that better be secure, and there are some applications that might not be. I use the analogy in the auto industry, right? The in-vehicle infotainment system, right? Spinning graphics, music, all the good stuff that you get, maybe not so secure, but if that screen shows you a rear view camera, all of a sudden that's a safety critical application. So the integrity operating system runs on a lot of Audi in-vehicle infotainment systems built by Bosch. And there's a separation in there where we virtualize one OS, like a Windows OS, or probably in their case, it's Android. And then the safety critical applications run on another partition on the integrity operating system. And a lot of the technology Albert uses in his system is separated like that.
Hi. So my name's Darren Blue. I'm from Intel in our Industrial Solutions division. One thing I would add to that is, you know, everything that was said earlier about the hardware root of trust, we fully endorse that and believe in, you know, those sort of standard procedures and, you know, role-based authentication and those types of things. We also work with the other architectures in, you know, for one example is secure device onboarding. So, you know, creating sort of a common approach to how security is done, you know, is something that we're, you know, looking at making ubiquitous across the computing environment, not just even Intel processors.
Okay. Another question? From anybody? No question. Was it, I didn't. I'm amazed. I didn't think the topic was quite that complex, but or maybe too simple. I don't know. Anybody have any other comments based on our panel here that they'd like to take the opportunity to elaborate on or expand on, or anything that we've covered here? Maybe I'll just sort of make another comment here about the, at the end of my presentation, I talked about, or I alluded to the convergence of these three technologies of AI and its various subsets of 5G, which is just now emerging and hitting the overall industries in general, and of course the IoT, and how they're basically kind of all maturing at the same time. I think just to maybe elaborate on that, there'll be some debate with 5G and the effect it'll have in the industrial environment. That debate's going to probably center around latency as we get down into those areas of controls and automation, and the actual time that's involved in microseconds and instantaneous controls environments and so forth. So I think that's probably going to yet to be resolved. I do think that 5G will probably have will mitigate that the latency period to a certain extent, but it depends on what level you're talking about. But I think overall, I think the areas of how we manage the data, how we're going to deal with it, the huge amounts of it, and then how we're going to deal with it securely. I think those are the main issues, and I hope that that's basically the takeaway here. That number one, we're going to be dealing with a lot of data. Number two, and I think Henning made this point in his presentation yesterday. It's basically about the quality of the data or the context of the data. If you're not going to be able to the best, most functional training algorithms if you don't have. Okay,
you have a
I'll
question.
interrupt my spiel here for a second. We got a question back there?
You can go ahead and finish the thought.
Yeah, okay, what I was gonna say is the context of the data is gonna be extremely important. It goes back to the old fundamental garbage in and garbage out. Is if you use his example of the timestamp and everything, if that's the context you're working in, we're gonna need a lot more than that. And it's gonna have to be predicated on aggregating and organizing and contextualizing the data, and that's going to be another effort altogether. In addition to the managing device management overall, and the amount of data that we're dealing with, the amount of inferencing that's done at the device, and of course the security that has to underlie it all. So anyway, go ahead.
Thank you. David Kling, I'm business development at Intel. So question for Henning, you talked about these IPCs, 45,000 or a big number. And I think of the PC refresh that I see us do at Intel and probably other corporate companies. We're all used to this kind of pretty standardized cycle. Is there a timeline that you see for the refresh of those devices? That end state you kind of showed, you said you guys aren't there yet, but how do you envision that timeline going? And are there people and processes and tools that you think are priorities to make that easier?
There are several layers to that answer. First of all, again, thinking in the old way automation thought, you bought the box to live with the process as long as the process runs. That's the old way of thinking, because you buy this box, it controls that process, so the box is completely fine to control that process, period. No need to change. And then enters IT security, whatever, which makes you wanting to update operating systems and these kinds of things. Which then a new operating system may be requiring higher compute capacity so that it runs fine on this computer. In the end, I think the thought how these PCs were installed is they are sitting there until they die, and then we'll replace them by a new one. Every 7 years, when we install new car models into our factories, they'll get replaced. But so that's basically the time frame which we plan on replacing those PCs when installing, anyhow investing into a new lineup for a new car. Then we'll replace the compute hardware as well. This concept I just showed will actually go down a little different route, because you'll during your production process, we'll start learning to do more and more with the data out of our production processes. We'll have more and more insight on what this process is actually doing, what the data is doing. The need for more compute will probably come up, and will either replace the PCs or add more compute hardware in order to do these algorithms and to steer our production lines. I have no idea what timescales that will be or how it will go. In the end, I think I'm not quite sure whether this sounds correctly translated into English, but it's something like the appetite comes with the eating. Once we started down this road and we figure out what else we can do in order to optimize our processes and save money by just adding a little bit more compute, that's something we will do. So this is, I hope, part of the answer to your question.
Hi, Dave Lafferty, IXN. With the advent of the software, defined, controllers and running on, commodity hardware, then where are you guys at with an infrastructure as a service where you don't even own the hardware anymore, and that you you pay by the service rather than the hardware?
Yeah, that's something I'd like to get to. I think automation as a service, Uberize it, all that goes away. If you have a nice big checkbook and just come over and see me a little later on, you'll be the first. It's a natural evolution, I think.
You're seeing a lot of like in smart buildings now.
Yeah.
And things like that. It's almost the electrification, but in the process industry, we just aren't seeing it really sound much.
Yeah.
I think it's a transition process, and there are things where you'll just do automation as a service. There are other things where, for IP reasons or for whatever reasons, you want to do this yourselves. Right now, in at least in our world, the colleagues from automation, they want to have something they can touch. It's still this, I get the function, I have a box, I want to touch it, I want to open up a cupboard and see, yes, the PLC is right there. And if something breaks down, I'll just tear this out, take the SD card out of the PLC, put a new one in, push the SD card back in, and the process runs again. That's the way we repair. And if all of a sudden this stuff is virtualized, how do you perform this repair task? You have to train your people that things work a little differently. You spin up a new container, a virtual machine that does all that. So I think it will take some time. It will take some time to understand that maybe for an assembly line, the compute power, all the compute power you need is just one server sitting somewhere in a data center. Because actually the cabled latency is good enough in order to do that. Yeah. Can we persuade our people to do this today? Heck no. But we know this is the path that we're going down, and then we'll see where it will develop to.
The number one cost in life cycle is obsolescence, right? Say you pay your vendor $100,000 a year or something for software maintenance, upgrades, and so on. And 10 years or 20 years, you paid them $2 million. And then you get a life cycle, end of life, Dear John letter from them, and it costs you $20 million to replace it. So that's the thing you want to solve, right? That's the thing we approached. So automation is a victim of semiconductor obsolescence, more so now than ever, because a system will go obsolete because a chip goes obsolete, because the chip cycle is a fraction of the automation cycle. So our model is different because we design, engineer, manufacture, and own every single piece of silicon that's in the box, because we're a division of a semiconductor company. So we give guaranteed non-obsolescence. So that really disrupts that whole idea. Now, adding some sugar to that, saying just one cost, you don't even buy it, you're fundamentally leasing it, and you have integral, indefinite support, security, firmware, software, application, network, hardware, upgrades forever and ever until you shut the whole thing down. I think in upstream oil and gas or any part of process automation that's highly commoditized and it's just driven by the CFO, then that's more likely. I'd like to get there, but not yet.
I have a two-part question. The first one maybe to the gentleman from Audi and Intel. I mean, question is whether you're starting to see industrial applications of these AI chips, and what are they? And second part is to everyone, as the compute power of these AI chips continues to grow, where do you see the need for cloud? I mean, why can't you train the models locally at the edge itself as these chips start to penetrate into the automation and edge systems?
Should I start?
Yeah, go ahead.
What we are using the specialized chips for is for pattern recognition. So the question always is, where do we have instances where we have optical inspection of our process? Can't we automate this optical inspection and then use a pattern recognition chip to just do this much quicker than sending the data somewhere? So this is where we see a use for those chips, and it's where we are already using them. In the end, the question will be, again, to this general compute hardware. If your application, if the case you're trying to solve requires you to have specialized compute power in this generalized hardware, then you may not add 2 or 3 more standardized PCs, but you may add a compute accelerator, an FPGA card, and inferencing unit. So these parts for me are still part of a generalized hardware that help you in your process. So I don't think there is a general answer to that. It's rather, what problem are you trying to solve? And what kind of compute do you need in order to solve that task? And then figure out how to do it.
Yeah, and I'd add a little bit to that too. So as we look, Henning talked about one use case. We talked with him yesterday. Most of what we've seen so far is in sort of the quality inspection and how do you learn sooner that the part's going to be good or bad. And a lot of that actually has been implemented, as he said, through video. And so it uses a general purpose compute or one of the FPGAs that can tie to that if it needs to be faster or multiple streams. And so when we're starting to see in the Audi case was actually pulling real process data and using that, so there wasn't a camera necessary. So we're seeing both of those, but primarily in the quality of what's being produced. How soon can I find out that it's good or bad, and at the same time increase the accuracy? We've seen a lot of deployments actually in PRC where they're moving away from sort of a human inspection to a camera inspection. Not only is it much faster, but it also increases the quality. One of the interesting ones is, they're taking a video looking at a transfer case, if you will, and they can tell whether all the holes are there, whether they're the right size, all that in, matter of seconds, while the part just comes straight out of the die. So it's still hot. So even a person couldn't inspect it yet, and they know whether it's good or bad, and the level of accuracy is significantly increased as well.
Interesting.
Hi, thanks. Mark Blackmer from Cisco. On the security front, I'm curious as to what the panel sees coming down the road when we look at, on one hand, I'm certainly pro encryption wherever possible, but then what you get into, especially in manufacturing and on the industrial side of things, is the latency issue. So it's one thing to decrypt and re-encrypt. So I see, at least down the road, if encryption is becoming adopted within industrial communications, what do you see as the impact to security being able to do anything in, say, real-time monitoring or anomaly detection?
Yeah. So if you are encrypting the comms, you can't do deep packet inspection because you can't see it anymore. So it's your choice, right? If you have a tightly coupled, closed comms between the devices, you can decide whether you want it authenticated and or encrypted, so you make that decision. But hardware accelerators, transistor-based hardware accelerators can encrypt and decrypt, do the math in milliseconds, fractions. So it's not really a problem from speed. It's really a question of whether you want the data to disappear. Yeah.
Okay. Excuse me. So we're coming right up on our time, and we won't want to keep everybody from lunch, but, so I think that unless we could probably squeeze one more question in if anybody has any burning question left here. And if not, then we can go ahead and adjourn and let you head towards lunch. But thank you all very much for your attendance. Appreciate it.